but it's my great pleasure to welcome Caprice Phillips to the Exoplanet Seminar. Thank you, Caprice, so much for coming out and talking to us today. Caprice is a rising fourth year at the Ohio State University, working with Dr. Ji Wang on the detectability of biosignatures with JWST and Twinkle. And she also works with Dr. Jackie Faraday on the atmospheric retrievals of planetary mass brown dwarfs to understand their formation pathways. So Caprice, thank you again, and I'll turn it over to you.
Okay, awesome. All right, let me share my screen. Okay. Okay, everyone, can you see my slides?
Looks great.
Okay, cool. All right, let me just figure out the best place to put Zoom. Okay, I guess it's on the left. Okay, anyway, so hi everyone. So thanks for having me. So as Joe was saying, my name is Caprice Phillips, and my pronouns are she, her, and hers. And today I'm going to be talking to you guys about the work that I've been doing with my advisor, Dr. Ji Wang, here at the Ohio State University, involving detecting potential biosignatures in the atmospheres of gas dwarfs with JWST. So before I start, I just wanted to introduce our collaborators. So there's my advisor, Dr. Ji Wang. We have Sarah Kinju at Space Telescope Science Institute, who's an expert on the MIRI instrument. There's also Tom Green at NASA AIM, who's an exoplanet and near-spec instrument expert. There's Renyu Hu, who is an expert on photochemical modeling. And then we also have Joe Schultz and Wendy Pinero, who work in the Earth Sciences Department, been really helpful in that aspect. And also Jeff Valenti, who's a near spec expert as well at Space Telescope. So it's been really great working with them and collaborating with all of them on this project. So I wanted to give a little talk outline of like how the structure of the talk will go today. So I'm going to start with the background of gas dwarfs and Haitian worlds, if you're not familiar with those, and then go into talking a little bit about atmospheric biosignatures, ammonia as a potential biosignature, going over some previous studies that people have done on gas dwarfs, atmospheric studies, then talking about detection of ammonia in these atmospheres of gas dwarfs, followed by talking about how I simulated the observations for JWST, and then talk about some of the future and like current work I've been working on involving the Twinkle space mission. So if you aren't familiar with gas dwarfs, you might be wondering, like, what are these things? So there's a study by Buck et al. 2014 that broke up planetary regimes based on the host star metallicity. And so they found that there were three main areas. There are planets that were below 1.7 Earth radii. They said these were terrestrial planets, and planets above 3.9 Earth radii. They said these were ice or gas giants, but between 1.7 and 3.9 Earth radii, they said that these objects were gas dwarfs, which they defined as planets with rocky cores with hydrogen and helium envelopes, shown here in the blue. And so what's really interesting about gas dwarfs is that they can encompass both super Earths and mini Neptunes. So what we have here is a plot here showing the number of planets versus the planetary type or size. Sorry, I'm just like trying to move Zoom in a better spot. The number of planet versus like planetary size and type, known planets by size, transiting planets. And so we know that super Earths and mini Neptunes are some of the most abundant type of planet that we know. We know this thanks to Kepler. But what's interesting is that we know little about their atmospheres and structure, and consequently their potential biosignatures. And so one of the other type of planets that is of interest for this study and future studies is something called Haitian worlds. So basically, I love including GIFs and stuff in my talks. And so basically what you would have is you'd have hydrogen H2 plus ocean or water. And so this was a study done by Medusadon et al. 2021. And so you get out something called high stream worlds, which is a cool way of combining hydrogen, H2 plus ocean, high stream worlds. And so basically, Niku said that essentially these are planets that allow for large oceans with habitable conditions underneath an H2 rich atmosphere. And some of the examples of those include a target K218b and TOI 270c, and these are some of the gas dwarfs that were targets of interest for this study as well. And so, as I mentioned before, like gas dwarfs include super Earths and mini Neptunes. So what's interesting about them also is that we don't have an analog for them in the solar system. So we ideally we have a very structured solar system with the inner rocky planets like Mercury, Venus, Earth, and Mars, the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. And so looking at gas dwarfs, it kind of begs the question, are they scaled up versions of the inner rocky planets, or are they like scaled down versions of gas giants, and like what stopped them from becoming gas giants? And it brings again the question about their formation, habitability, and potential biosignatures. All right, so kind of moving on that background of gas dwarfs and high stream worlds, I wanted to go in and just give like a brief overview of some of the things about atmospheric biosignatures. If you're not familiar with what a biosignature is, so Meadows and Seeger in 2010 defined atmospheric biosignature as a gas whose presence in the planetary atmosphere indicates that the planet likely harbors life. And so they kind of came up with three main criteria. The first one, you want it to be generated by life, built up in the planetary atmosphere to be detectable. You want to have enough of it. And of course, you want it to be present / active and the wavelength range being observed, for example. And so they then went on to talk about like what makes a biosignature like ideal, for example. And so one of the ones is that, you know, you don't want it to exist naturally in the atmosphere at ambient temperatures and pressures, for example. Two, not created by, you know, geophysical processes like volcanic activity. Not produced by photochemistry. Not significantly destroyed by photochemistry. And also, of course, again, we want it to have a strong spectral feature, for example. So that's just like a quick overview of atmospheric biosignatures. So I wanted to go in and start talking to you guys about ammonia as a potential biosignature. So just a little brief background about ammonia. So Fritz Haber won a Nobel Prize in 1913 for the Haber-Bosch method, is where you take nitrogen from the air, combine it with hydrogen with really high temperatures and pressures, and a catalyst like iron to produce ammonia. And that's the main industrial production of ammonia on Earth. So this is just a schematic diagram of that process. And this is the formulatic chemistry for how ammonia is made for this process as well. And so when you traditionally think of ammonia, you may not think about the Haber-Bosch process. You may think about, oh, okay, ammonia is in cleaning supplies and it can be really stinky, for example. But I wanted to introduce you guys to the idea of ammonia as a candidate biosignature gas in an atmosphere rich in hydrogen and nitrogen. So this idea was first proposed by Sarah Seeger in 2013. The idea is that in an atmosphere rich in hydrogen and nitrogen, that microbial life can catalyze the breaking of these bonds to produce ammonia, capture the energy release, and produce an excess that would build up into atmosphere to possibly detectable levels. And so what's interesting about this is that this reaction doesn't happen under 1300 Kelvin and needs a catalyst for it to happen. And so Sarah Seeger proposed ammonia as a strong candidate biosignature in this hydrogen-rich atmosphere for the following reasons. They said that, again, that it's a exothermic reaction, meaning that, you know, a heat release microbial life could use for metabolic processes. That's the first one. Two, you need really high temperatures and pressures in abiotic environments to create ammonia, meaning that if you were to see the ammonia in the upper atmosphere at ambient temperatures and pressures, that would indicate that something could be causing the ammonia to be there. And third, so it's easily destroyed in photochemistry in volcanic environments. It doesn't like to be there. So if you were to find an indication or find some ammonia in the atmosphere, that could be a sign that something is continuously producing it and making it in the environment, for example. So Sarah Seeger nicknamed these worlds cold Haber worlds after the Haber-Bosch process. And so this is a theoretical emission spectra of a cold Haber world, one where there's 75% nitrogen and 25% hydrogen in the atmosphere. So we have here on the planet irradiance on the y-axis, and the wavelengths range from 5 to 30 microns on the x-axis. And so what we see here is the black line is that there's no ammonia in the atmosphere. And then when we go and we increase the amount to like 0.4 ppm, we start seeing these features start popping up around, around 10 microns and 6 microns, for example. And then when we increase the amount of ammonia times 10 to 4.0 ppm, we start to see an increase in the strength of the line. And then we also see it here around 6 micron as well. So this is the basis and the start and the inspiration for this work as well. And so in another paper in 2013, Sarah Seeger was really on it. They're always on it. They're always writing papers. And so they also modeled how a theoretical transmission spectra of a cold Haber world might look. But this time they considered an atmosphere with 90% hydrogen and 10% nitrogen, as opposed to that 75% nitrogen and 25% hydrogen. And so basically what we have here is a plot showing the theoretical transmission spectra with the different sources of ammonia here and the near, mid, and far infrared. And so what's important about this plot is that, again, the black line is like there's no ammonia in the atmosphere, 0 ppm, for example. And so as you slowly increase the concentration of ammonia in the atmosphere from 0.5 to 5 all the way to 500, you get an increase in the transmission signal and the strength of the signal. Here, for example, you can see that it goes up as you increase the amount of ammonia in the atmosphere. That was, again, inspiration for this work as well. And so I would be remiss if I didn't mention that there are false positives for ammonia. And so Evan Sneed in their undergraduate thesis, they're currently a post back at Penn State, they talked about ammonia being brought through collisions to the planet from ammonia ice from comets. And then Sarah Seeger in 2013 also laid out 3 main sources of like abiotic ammonia. So the first one being a rocky world with a hot surface temperature of 820 Kelvin that could produce ammonia maybe through the traditional Haber process. And then there's also can be naturally occurring ammonia in the atmosphere of gas giant planets and mini Neptunes. And then there are planets that might have secondary atmospheres of outgassed NH3 or ammonia during evolution as well. So I did want to bring that up to put it into context. So again, when I mentioned ammonia, like those of you who aren't familiar with the idea of ammonia as a biosignature might associate it with the example of brown dwarfs with the dominant form of nitrogen in the atmosphere is ammonia in cool T and Y dwarfs. And there's also naturally occurring ammonia and gas giants like Jupiter, but this occurs at really high pressures in Jupiter's atmosphere, for example. So I don't know what that meant, I'll let you do there. So that's a little bit of background about ammonia as a potential biosignature. So now I wanted to go and talk about some of the gas dwarf atmospheric studies that have been done on this topic as well. So the first one that I wanted to talk about was the study by Chakor et al. 2020. So basically, essentially, they investigated the atmospheric properties of the TOI 270 system and the capabilities of JWST to detect and characterize the system. And so one of the purposes of the paper is they wanted to test how many transits were needed to test to see if there was an atmosphere and to see if they could detect molecular features like ammonia. So shown on the right here is a plot of one of the targets that I mentioned before, TOI 270C, where they simulated a clear H-rich, hydrogen-rich atmosphere, and also one where it has a cloud deck at 10 millibar. And so this is a transmission signal on the y-axis, and the wavelength coverage from 0.8 to 5 microns, covering the near-res SOS instrument and the near-spec 395 M mode, for example. And so one of the things that I wanted to point out is that they're showing the main molecular features that would be here, like methane, water, and ammonia. And so they found that for the 3 micron ammonia feature, you would only need 1 transit to detect this feature at a 5 sigma significance with the near spec G395 mode. And so they also found that for the around 2 close to 2 ammonia micron feature, that you would only need 1 transit to detect this feature at an 18 sigma significance. And so they use like similar techniques to ours, but the difference is that their mean molecular weight is about half of what we calculated. And so next up, I wanted to highlight the study of Wunderlich et al. 2020 that looked at the detectability of biosignatures on one of the targets for this study, which is LHS 1140b. And so basically what they used was the radiated convective photometric climate couple model 1D Terra. And so they wanted to see, like, with certain instruments like near spec prism aboard JWST, be able to detect potential biosignatures. And one of the ones they looked at was the 3 micron feature of ammonia. So essentially, this plot on the right, what they found is that if you have like a 90%, if you go over here to like 90% hydrogen volume mixing ratio, you would need about 10, 20, 30 transits, which is about 180 hours of observing time to detect ammonia at a 5 sigma significance level. And that's with a 90% hydrogen-based atmosphere. And so another one that I wanted to talk about was the work by Evan Sneed, who looked at the climate investigation of ammonia's remote biosignature on Cold Harbor Worlds Part 1 and 2. And so some of the really interesting questions that they're asking is that they want to know about the pressure temperature profiles of Cold Harbor World planets. They're asking questions, really good question about like how long does hydrogen last in the atmosphere, and what conditions allow for the detectable buildup of ammonia in the atmosphere, such as the surface temperature conditions, for example, which are really good questions and things to take into consideration for the context of work like this. And lastly, I wanted to highlight some recent work by Huang et al. 2021, which looked at the assessment of ammonia as a biosignature gas in exoplanet atmospheres. They wanted to investigate the feasibility of ammonia as a biosignature on terrestrial-like planets, and as JWST would be able to detect the feature. So ultimately, they found that you would need a concentration of like 5 ppm ammonia in the atmosphere for JWST to be able to detect the features. Excuse me. Okay, so now moving on to what I did, the detection of ammonia in the atmospheres of gas dwarfs, after we've gone through some of the background about biosignatures, gas dwarfs, and ammonia as a potential biosignature. And so we've covered a lot of background talk. And so I just wanted to remind y'all of the question that we were trying to ask is, can JWST detect ammonia in the atmospheres of gas dwarfs? That was the main driver question that we were doing for the study. And so before we, as we got into the study and before we could begin the study, we of course wanted to select kind of optimal or ideal targets for this work. And so we had 3 main selection criteria for targets that we use from the NASA Exoplanet Archive. And so the first one was at equilibrium temperature less than 450 Kelvin. We wanted to be between 1.7 and 3.4 Earth radii, and then less than 50 parsecs away. And so the equilibrium temperature is where liquid water can exist at 10 bar pressure, and the lower radius cutoff is to make sure that the planet has likelihood that it will have an atmosphere, and the higher cutoff is that the pressure won't be too high to produce ammonia abatically. And lastly, the less than 50 parsecs away, we want adequate flux between the planet and the host star. So this plot on the right here is showing the planet radius versus equilibrium temperature, and these are some of the targets that were picked based on the selection criteria for this study. And some of the ones I've talked about, like LHS 1140b and like TOI 270c and KG18b, are some of the ones that we looked at for the study. And the ones in the gray dots are just those that met the first two criteria with the temperature and size, but were more than 50 parsecs away, for example. And so we don't have the data for JWC yet, so we had to simulate the atmospheres. And so I used something called Petit Ray Trans. It's a radiative transfer model from Paul Molière in 2019. So basically, you can change things such as how much of the molecules in the atmosphere, like the abundances. You can play with things like the PT profiles, the surface gravity, the planet radius, mean molecular weight, what's the temperature of the planet, and you can account for cloud decks, etc. And so those are the model inputs. And so the model outputs, this is just an example of what Petit Ray Trans like outputs, simulated transmission spectra on the top and a simulated emission spectra on the bottom here. So this is the type of spectra that I would work with for the study. And so given our target size and distance, so the planetary flux that we receive will be incredibly low. And so this is a plot showing the different targets, the planetary flux in millijanskis from in the wavelength coverage from 5 to 11 microns. And so the ammonia feature that we'll be interested in seeing if we could detect to be this one around 10 microns here, and also maybe this one around 6.1 microns as well. And so so the targets, they're just color coded for like temperature. So as the equilibrium temperature goes down, we get less planetary flux, for example, which is an indication that it'd be really hard to detect these features with emission spectroscopy, for example. And so, oops, sorry. And so we used different instruments. One of the things that we wanted to test was like, which instruments would be the most ideal, like for certain targets for certain types of spectroscopy. So for like transmission spectroscopy, we looked at things like with the NIRSpec and NIRS instrument, and for like emission spectroscopy, we were looking at the MIRI instrument, for example. And so this is a plot here showing the, sorry, I'm just gonna move zoom to the side. So this is a plot here showing the flux contrast for the planets, for the targets, and with the 5 to 12 coverage for the MIRI LRS instrument. And so the dotted line is the systemic noise floor for about 10 transits, which is a baseline number of transits that we used. And so from this plot, we can see that there are only a few targets that are above the systemic noise floor for this instrument, meaning that they would need to be above this line basically to be detected by MIRI LRS, which is just, it's challenging regardless. And so if we were to take like the one that has the highest flux contrast, and this one here in the brown here, and so if we like zoom in on this, and we can see that even though it's above this systemic noise floor, it's still limited by like photon noise, which affects the detection. So it'd be really hard and difficult to detect this around 10 micron feature here, even though it is above this noise floor limit. And so kind of like one of the things for the study, because like when we're seeing that originally the MIRI LRS instrument like doesn't look like it would be the optimal for it. I was like, oh shoot, like it's over, the project's over. My advisor's like, no, there's a lot of ammonia features in the near infrared. So that's where we turn to. And so one of the things that I learned, and part of the progress for this study, is that it's like just as important to kind of rule in targets as it is to rule out targets and instruments that would not be the most optimal to make best use of JWST time. And so as we turn to the near-infrared, we see that there are a lot of features to look for. So this is a plot just showing the ammonia features in the near-infrared. There are strong ones around like 1.5, 2, like 2.3, and like 3 microns, for example, that we were interested in looking at, for example. And excuse me. So also we, in part of the paper, we did a retrieval analysis. And so we saw that even though there are some features that are close and they may overlap, that ammonia and H2 and water can be like retrieved like independently, for example, in one of our targets that we zoned in on, which is TOI 270C. And so one of the things that we did for the paper and for this work was that we wanted to explore like how like the change in the concentration of hydrogen in the atmosphere affected ammonia detection, because in the previous work that I mentioned, Sarah Seeger looked at ones with 90% hydrogen and also 25% hydrogen. And so when we turn to things with transmission spectroscopy looking in the near infrared, so this is a case for the 90% hydrogen. So what we're looking at is the transmission signal on the y-axis over here with the wavelength coverage showing the different JWST instruments and modes. And so basically what we have here in the orange is a theoretical spectrum for TOI 270C, and this is for 10 transits. And so we use the Pendexo tool by Natasha Batalha to simulate observations and the noise floor for JWST. And the simulated observations are shown here in the black data points, for example, and this is for a baseline of 10 transits. So for example, if we were to look at the 1.5 ammonia feature here, and we can go down and see how the signal to noise looks, we see that we get a signal to noise around 5 sigma for 10 transits, which is a good sign that indicate that this feature might be able to be detected at a 5 sigma detection level. However, if we go over to, and I'm going to zoom to the other side. So if we go over to a 25% hydrogen atmosphere, if we looked at the same ammonia feature for the same target, same number of transits, using the same instruments, we see for the same 1.5 feature that we would get a signal to noise of around 2 sigma. So for example, so it nearly like cuts in half the signal to noise as we decrease the amount of hydrogen in the atmosphere. And so one of the other things that we wanted to look at to see how it would affect the signal to noise for detection for ammonia, if we want to see if you change the concentration of ammonia, like how that would affect it. And so basically this is similar to the work that Sarah Seeger did. So we like kind of varied it from 0 ppm all the way to 400 ppm. And so again, what we saw is that basically the concentration of ammonia in the atmosphere, which is proportional to the biomass or material on the planet, changes the transmission signal. So basically, if you have a stronger signal, that could be an indication that there's more biomass or material producing this ammonia signal, for example. And so if you have a weaker signal, that maybe indicate that there's less things producing ammonia on the planet, for example. And so also one of the things that we have to account for is those pesky little things called clouds. And so we simulated how adding different cloud decks at different bars in the atmosphere would affect the transmission signal for the targets as well. And so basically we found that, again, like clouds weaken and hide and weaken ammonia features. So if you have a cloud that's higher up in the atmosphere, you're getting into this flat spectrum here versus a cloud that's lower in the atmosphere, you get a stronger transmission signal, for example. And so basically some of the culmination for this work was that we came up with a ranked list of targets. And so we ranked the targets by and quadrature sum of the total signal to noise for the ammonia features. And so one of the highest targets, which is the one that we use as the base case to simulate, was TOI 270C. And the last one that ranked last was like GJ 143B, because its host star is too bright and would like saturate the detectors, for example. And some of the ones that were of interest for the study in particular are LHS 1140B and K218B, who have more precise mass and radius estimates. We can give you information about the interior to put the context of detection versus non-detection into context, like for the planet, for example. And so the paper is, it's out now, it's out in the archives, it's recorded so people can put their phones and scan it to the paper. But I just want to let you guys know that the paper is out. And so basically this is a summary of the work. So basically we found that gas dwarfs, which includes super Earths and sub-Neptunes, are really interesting targets to search for potential biosignatures, and ammonia can be a potential biosignature in hydrogen and nitrogen down in atmospheres of gas dwarfs. And we found that it's more ideal for transmission spectroscopy, where the near spec and near res is better suited to detect ammonia than emission spectroscopy with MIRI LRS. And so one of the things we also looked at was how ammonia detection was affected by clouds, how much hydrogen in the atmosphere, and the amount of ammonia in the atmosphere, for example. And so I'm kind of continuing a little bit of this work with some smaller targets with the Twinkle space mission. Excuse me. So I wanted to just briefly tell you guys about kind of what I'm working on now with the Twinkle space mission. And so if you aren't familiar with Twinkle, so it's a space mission that's supposed to launch, I think in like 2024 or 2025. And so these are the schools that are kind of the founding members for it. And so it's ideas that it's supposed to, one of the things they wants to do is to search for potential habitable worlds, and so focus on exoplanets and solar system objects, for example. And so this is a map showing Twinkle's field of view, showing the known targets and test predicted targets distributed by the size of the planets, with the green being less than 3 Earth radii, the blue being between 3 and 10 Earth radii, and the red being the ones greater than 10 Earth radii, for example. And so I'm a part, for the Twinkle mission, I'm a part of the Sub-Neptune and Super Earth working group. And so these are some of the questions that we're interested in seeing if we can answer. You know, one of the ones like, can we detect potential biosignatures like ammonia in the atmospheres of hydrogen, helium dominated temperate planets? We're interested in exploring the radius valley, like primary versus secondary atmospheres, and then also exploring clouds and haze properties and sub-Neptunes and how this changes with temperatures. And so again, I'm kind of focusing right now on the first thing about potentially detecting ammonia in these atmospheres. And so kind of some work that I've been doing is kind of seeing if Twinkle, like what ideal targets would be best for like the Twinkle space mission. So I've been exploring targets like based on different selection parameters, kind of like going a little lower in the planetary size to see maybe if these smaller type planets can like hold on to a hydrogen-based atmosphere, like could we detect ammonia in the atmosphere. And based on the work by Wong et al. 2021, seeing if like these smaller terrestrial like planets where ammonia could be a potential biosignature, like seeing like what we see like in the atmospheres, for example. So this is a plot showing the planetary radius versus equilibrium temperature for one of the targets of interest, LTT 1445 AB, below the Fulton gap. And so one of the other things that we're also looking at is maybe looking at the interior structure of some of the targets. For one of the targets, so this one has a more precise mass and radius estimate. So seeing what the maybe using models like exoplanets that I've been working with Romy, grad student at OSU to do the interior modeling analysis for this target. So that's something we've also been working on right now. And so basically, like, I'm also estimating the signal to noise for this target for Twinkle as well. And so because it's a smaller type target, we had to like up the baseline transits to like 25 transits, for example. So this is a simulated Spectra, again, using petite. And so basically, we see that like even with 25 transits, you would get like below, like this ammonia feature around 1.5, like you would get like below like a 2 sigma detection level for this specific feature. So it's kind of exploring like what that looks like and what like we may see with Twinkle. And so earlier I talked about high-Sheehan planets, and so LTT 1445AB was listed as a potential high-Sheehan planet by Medusodon et al. 2021. And so we've been working to see like a two-pronged approach where like can Twinkle distinguish between like a cold harbor world versus a high-Sheehan planet, because they're based on the type of planet, they may be different biosignatures or potential biosignatures on this planet. So we're seeing that it could using the reduced chi-square analysis that it might be able to distinguish between the two. And so one of the things that we're also doing with the interior analysis is like seeing if like that can like explain like given like the density and stuff for the planet, well, like is it actually a high-Sheehan planet or not, using like updated mass and radius measurements. So that's one of the things that we're also kind of experimenting with right now, which is really cool and exciting. So yeah, so I'm nearly at time. I want to say thank you all for listening to my talk, and I'm also a part of Black and Astro, and we have our Black and Astro week coming up starting on Sunday. This is June 19th to the 25th. So thank you for listening, and I'll take any questions that you have. So thanks.
Thank you so much, Caprice. That was an excellent talk. Really, really interesting work that you're doing.
Thank you.
So if anyone wants to ask any questions, please feel free to post them in chat or raise your hand. It looks like we do have one in chat. So let me just read that out loud. So Max is saying, the inclusion of clouds in your model was a nice addition. I'm assuming that the prior synthetic spectra before the mention of clouds assumed a gas phase ammonia. In cases of clouds, depending on the temperature profile of the atmosphere and the cloud height, might the ammonia be liquid droplets instead of gas? And if so, that will presumably broaden and shift the ammonia absorption compared to the gas phase. Have you looked into that at all?
No, that's a really good question. No, I have not considered that. I'm actually going to screenshot this so I can like have it for later. So I'm really bad at remembering things, and I brought a pen to write it down, but it's easier to screenshot it. Anyway, so no, that's not something we've considered, but that's a really good question. So I'm going to bring this up to my advisor. So yeah, thanks for asking that, but I haven't thought about that.
Awesome. It looks like, okay, I think Avi, was that kind of a response to the previous question that was there. So yeah, anyone is welcome to raise their hand or just go ahead and unmute and ask any questions. I wanted to ask you, Caprice, when you're looking at the different amounts of ammonia in the atmosphere, like you had that plot showing, 0 all the way to 400 ppm. Do you know, like, if there's a certain ppm level where you start to rule out some of those false positives you mentioned earlier on in your talk, like the other production pathways for ammonia? I don't know if there's been any work done that says that, like that surface, that really hot surface false positive, if it can only produce so much ammonia.
Yeah, no, that's a really good question. So one of the, I had talked to one of our collaborators, Ren about like what concentration of ammonia like would make sense for like these type of planets, for example. And he said like up to like 10 like ppm like concentration. And so there's also been I think it's John Sucre. I'm messing up the name, but there's a paper, Rajan, I think was the last or first name, that looked at something called like photochemical like runaway, and these like type of planets, and like if there's like a certain, if like the material on the planet is like producing a certain amount of like ammonia in the atmosphere, like it can exceed like the amount that's being like destroyed by photochemistry, you can have an excess of ammonia build up into the atmosphere. And so he had listed like a certain ppm, which I'm like losing the amount right now, but there can be like a larger ppm if there's like a larger concentration of ammonia if it enters something called like photochemical like runaway, like in the thing. It was a study by like Rajan, I think, et al. 2022, where they're looking at things that could create like an additional excess of ammonia in the atmosphere, which is something that we're like looking at for like Twinkle with the next work with Twinkle 2. So I don't know if I kind of answered your question or just totally went on like a runaway, no pun intended, runaway trail type thing. So but yeah, so that's something that that I've been thinking about as well, I guess, long story short, I should say.
No, that's great. That's great. Thank you so much for answering.
Yeah.
It looks like Avi asked a question in chat. Have you looked into detecting ammonia in near IR direct imaging with ELTs? The 1.5 micron region is directly in the sweet spot for the expected imaging and spectroscopy of M-star planets.
No, wow, you guys are asking really great questions. No, I haven't. Oh yeah, G has done some of this work. So right now I'm just looking at like space-based stuff with like JWST and like Twinkle. Like I don't know if there are plans to do that, but kind of like I mentioned, the next phase that we're trying to use Twinkle as kind of like initial, like you may be able to initially characterize it with Twinkle and maybe do follow-up stuff with JWST. But no, I haven't heard any mention from G or anyone we're gonna do like ELTs or anything like that. Maybe we are, and this is like news to me or something like that. So yeah, no, that's a good question. So
awesome. And I was just curious, like, what your thoughts are kind of on just the field of biosignature detection moving forward, because this is not my area of expertise, but it really seems like eventually, if we're going to make some, discoveries of potential biosignatures on a planet, we are really going to need like a suite of different biosignatures to have any sort of confidence, just because the bar is so high to say that there's life out there. So, ammonia, this, from your talk, it seems like this is a great candidate of a biosignature. You did show that plot where there was kind of some overlap with water features. So I was just curious, when you're looking at some of these spectrums, do you think there's going to be a point where it's going to be hard to distinguish between different biosignatures? Do you think that ammonia is a good like complement to other signatures? So if you see, water, for example, or some other biosignature, but it's not really enough to give you a lot of confidence, do you think that ammonia can fill in the gap and say like, well, there's also this ammonia feature too? So it's just a kind of another point in that direction. I don't know if you just wanted to expand upon that at all.
Yeah, so I guess kind of my interpretation of what you're asking me, and I guess what I have to say about it is that I think one of the things is like detecting like biosignatures, that you obviously have to be like very careful and very thorough with like what you're like what you're doing. And so like you'll want to like say if we were to like because one of our collaborators, when you who has like observation time for like K218b, and so say we go and we get some transits, and then like, oh, we maybe fine and can constrain the amount of ammonia in the atmosphere, like you can't like immediately say like we did it, we found it, like we answered the question. Like you have to like follow up, you have to do confirmations, and then it's also like just not as simple as that. Like you have to put it into context, like for the system in itself. Like each case is like a unique type thing, and then there's also each case is its own unique thing where you have to like, then you need to really start talking to people like Vicky Meadows and all the people like interior people, biology people, like all this type of stuff. And then like basically like based on like maybe how the atmosphere is, it's like if it is this type of planet, like in the Haitian world planet, like when they listed the different, I think they listed like DMS, which I don't know the full full technical name for it. Some chemistry thing I don't know the name for. But one of the like molecules where it could be a potential biosignature, like ammonia isn't listed as a candidate biosignature in hydrogen world. So if it's like indication that it may be like more water on the planet that could be like destroying the ammonia, like for example, like you have to like consider like those things like as well. So it's very tricky, and you need to, what I think is what's interesting about this field is that you get to like collaborate and talk with like a lot of different people to be like, does this make sense? Like given if this other molecule is present, like does this make sense for this type of planet? So yeah, that's kind of my long-winded answer of saying, I don't know. It's very interesting type of field and stuff. That's what I wanted to expand upon.
Yeah, that's great. Yeah, well, it was a very rambling question I had, so thank you for digging into it anyways. Does anyone else does anyone else have any other questions for Caprice? Feel free to raise your hand or just speak up. All right. Well, I am not seeing any. Caprice, thank you so much again for coming out and speaking with us today. This is really, really cool work, and I hope to have you at Goddard at some point in the near future.
That'd be awesome. Thank you so much. I'll stop sharing my screen.
Sounds good. All right. Well, I will go ahead and end the meeting there, but thank you all for coming out, and thanks again, Caprice, and I hope you have a good rest of your grad school. Good luck with everything that's coming up in the next few months.
Thank you so much.
All right. Take care, everyone. Have a good day.
All right. Bye.